Boom. Hello and welcome back to Calculus 1, Chapter 5, Section 5.1, Approximating Area under the Curve. It's going to be interesting. So we are going into Chapter 5 now to learn about integration, and we already know how to integrate from 4.9. The question is, what is so special about integration? We know that the slope of the tangent line was the special thing for the derivatives, and in application, slope of the tangent line measured the instantaneous change. So when you are working on application, you would say, okay, speedometer shows the instantaneous speed, which is velocity, right? Well, magnitude of velocity, and it changes as rapidly as you change the speed, obviously, right? So because it measures it. But now, what is that special thing for integrals? And the special thing for integrals is the area under the curve. Now, in application, that area is taking a lot of different, right, concepts on. We'll see that we are talking about accumulation. So we can talk about, on your project, you have the amount of rainfall. To calculate the amount of rainfall, you definitely need chapter 5 for that. Definite integrals. But then we can calculate accumulation, but also, it's the energy, amount of energy would be area under the curve. And then we can talk also about going backwards with acceleration and velocity and so on. And then, so any type of accumulation is going to be area under the curve. Now, you are all familiar with the fact that on the xy plane, if you just have a triangle that goes 3 up, this is 5.5 for whatever reason, 5.5. And if you want to find the area of this triangle, you can simply say that area is 1/2 base times the height, which is 1/2 base times the height. And you are going to get 16.5 over 2, which is 8.25. So we get 8.25 if we calculate the area under the curve. Now, if you have a different type of a shape, for instance, I don't know, let's go with a trapezoid. So this trapezoid has, this is 4, this is 5, and this is 2. So if you look at this trapezoid now, if you know the formula for area, which is 1/2 a plus b times the height, we just simply put 1/2 and then 4 plus 5 times 2, so the area is 9. Now you can see that area is 9 easily, on this picture at least, because you have 1, 2, 3, 4, 5, 6, 7, 8, and then these two together make a 9th square, and you have 9 square units. So that does work. We can also find 1, 2, 3, 4, 5, 6, and then the rest would make 8.25, right, in terms of these little triangles. So we have correspondence between the graphs and obviously the area. So if this is 1 and a 1, then the area is 1 unit squared, whatever that unit is. So we can approximate these things. Good, but we can calculate them if we know exact formulas. The hell breaks loose when you have a function like this. So what is the area under the curve between A and B now? Right? So you might want to be, you know, fancy and try different things, but these are curves. So would it fit, maybe find a max and then fit the over here some kind of shape and then find another one, I don't know, like try stuff. You'll see some of these things done in Calc 2. But I have a much better idea to propose here. What are we going to do if we have curve and none of the formulas that we learned for square, rectangle, trapezoid, triangle, circle, none of that works? What should we do? Well, we are going to cut into rectangles. So let's say we have our XY coordinate system, and now what I'm going to do is I'm going to create these rectangles. So I have x0, x1, x2, x3, and x4. Well, are these rectangles? No, they're not rectangles. What I can do is I can go and make them rectangles like this. Now they're rectangles. And if you carefully look, this point is f of x0. And that corresponds to the height for the first rectangle. The next point is f of x1, which corresponds to the height for the rectangle number 2. This point here is f of x2. This point here is f of x3. So now, if I take the first rectangle, I see that the length over here is clearly x1 minus x0, and the height is given by f of x0. So the area is f of x0 times x1 minus x0. Now we're not going to write this 15,000 times. We are going to see that since I have them equally spaced, we're going to see that x1 minus x0 is the same as x2 minus x1, is the same as x3 minus x2, is the same as x4 minus x3, right? Each one of these distances is the same, and we're just going to call that delta x. It's the change, the difference, right? The change in x. From x0 to x1, from x1 to x2, x2 to x3, and x3 to x4, they're all the same width, and they all have the same width there, which is, we're going to call it delta x. So now, if I look at my shape, right, each one of these guys is delta x. So in my calculation, that's delta x. So what's the better formula? Better formula is f of x0 times delta x. Delta x is a change in x. Now you would say, well, wait, this is way too easy for calculus. Why? Well, hold on, we'll get there. But this is it. Believe it or not. That's it. You cut the interval that you see, you cut that interval into some number of these divisions, right? x0, x1, x2, and so on. That gives rise to the rectangles, and you calculate each independent rectangle area, you add them all up, and that approximates. We have error. All of this that I'm going to color now is error. Right, that's error. That's error. That's error. So all of that stuff is error. the true area is going to be smaller than the one we get. But again, what we got is better than nothing, so we'll keep it, right? We'll have to keep it for now. I'm going to get rid of these. So let's take a look at example of this immediately and then improve on it. So say I have square root of x, right? So that's my function. And I want to compute area from 3 to 7. This should be closed interval because include 3 and 7. Area, let's put on. So area on 3 to 7. What should I do? Well, I draw the picture. Here's 3, 4, 5, 6, here's 7. And now I can use the divisions and try to calculate this area. So what I'm going to do is I'm going to drop these verticals. And then if you look at the board now, this is important. You get to decide whether you want to use this corner or this corner to draw rectangles. Note that the outcome will be different. Again, we are approximating. I'll zoom in. If I use the left one, the rectangles would look like this. See that? Do we all agree? If I use the right one, the rectangles would go like that, on top. Do we see that? This is why we have what we call the left approximation and the right-hand approximation. Sometimes it's specified, use left-hand sums, which means that your rectangles should emerge from each of the left points. Your rectangles, right? So this is the left, this one is the left, because see, when you look at any of the rectangles, the left point is touching the curve. So you make that choice on your own if it's not specified. If it is specified, you obviously use what's specified. So I had the choice and I chose the left ones, doesn't matter. So now, what's happening? Well, I have these other numbers, 4, 5, and 6. I also chose the amount of rectangles so that the delta x is 1, as you can see. It is cheap, right? The cheapest possible case. So what do I have? Well, for the first rectangle, let me label them. 1, 2, 3, and 4. So for rectangle number 1, area of number 1 is going to be the height, which is f calculated at 3 times delta x. Well, f calculated at 3 is root 3, and delta x is 1, because the difference between 3 and 4 is 1. Delta x is simply subtraction of smaller from bigger, right? Points. So we have that the area of the first rectangle is approximated by root 3. And now you can go and calculate the other 3 rectangles the same way. So area of the second rectangle is square root of 4 times 1, which is 2. Area of the third rectangle is square root of 5 times 1, which is root 5. And area of the fourth rectangle is root 6 times 1, which is root 6. Do not calculate, in this case, root 7, because there is no rectangle to the right of 7. So 7 can be the left side. So when you sit and think about it a little bit, it will be clear. So now, what is the overall area? It's going to be the summation of all other areas. So I have root 3 plus 2 plus root 5 plus root 6. And you can take your calculator and compute this. Let's say 2 decimal points should be enough. So we have a square root of 3 plus 2 plus square root of 5 plus square root of 6. 8.42. So area is approximately 8.42 units squared. I can calculate the exact area. Right? I can calculate the exact area, and we can see that we are not that far off. Just give me 1 second. I don't want to reveal the secrets, right? It's gonna be easier if I use this. So exact area, again, is going to be a decimal, so can't do any of this exactly. So the exact area is about 8.88. So as you can see, it's not perfect, right? It's not perfect, but 40 cents away, 45 cents away, we're good. Can't buy much for 45 cents, yes.
Well, I was going to say, how could you use the term exact and about? Okay.
Well, because I am multiplying everything by 2/3, which is 0.666666666, and I have to cut it somewhere. So exact area is about this because there are other decimals. After 88, it goes 2, 7, 3, 7, 8, 3, 6, okay. And then it goes on and on and on and on and on.
So
that's why I'm saying is about. And this is also about because all of these square roots, obviously, right? But, this method seems okay, right? We calculate left sums, we calculate right sums, and let's calculate right sums. For the same problem, let's calculate right sums. So we're going to take a look at same problem. Use right hand sums. We'll understand this right hand sums much better later. So I have again the same. This is terrible. Maybe I should sit down, right? This is 3, 7. And now for the right sums, we go to the first rectangle and go to the right side and draw the rectangle. So now you should be expecting your answer to be more than 8.88. Because, look, before, it was area that we calculated was less than the actual area. All of these, see this area there? That area was not included in our calculation. So now, when we calculate the same problem, we are going to get more. So now we have our rectangles 1, 2, 3, and 4. Area of the first one is going to be, now we are computing at the right hand side, so square root of 4 times 1, that's 2. Area 2 is square root of 5 times 1, which is root 5. Area 3 is root 6 times 1, which is root 6. And area 4 is root 7 over 1, which is root 7. So note that when we did the right sums, we never used 3, but we did use 7. So now area, I'll put R for right side, is 2 plus root 5 plus root 6 plus root 7. And that's going to go higher than what we were used. So let's see. And I'm getting 9.33. So now the right sum is that, and this means that the exact area must be in between 8.4, what do we have, 42? 8.42 and 9.33. Now I already told you that it is about 8.88, which is what we actually needed. So this is not exact. Why? It's called approximation. The question is, can we do better? Because we did 842, which is about, right, it's 0.46 away. Then you have 33 and 88 from the other side, about 45 away, right? So it seems that we are on both sides of the, can we do better? Think about it. Well, we can take the average, yeah, but can we do better with only one? Can we do better? And the answer is yes. We do better if we put in more rectangles. Think of a better resolution, all right? You take the picture with more pixels, right? And the picture is not pixelated, right? When I put up pictures for your exam, I make sure that in a Google image search I click on large on a filter. So it gives me large images. Otherwise, if I scale them up, get pixelated. So the same thing happens here. What we do is we dig deeper. We create more rectangles, Now I need to draw this really big so you can appreciate the resolution change. I want to sit down for this one. So now so this is my problem from before, and this is what I'm going to do. I know that I go from 3 to 7. Now instead of placing rectangle at every unit for convenience, I said, I'm going to sacrifice some of my convenience for better accuracy. So I'm going to get more rectangles in. I am technically doubling the amount of rectangles. I'm doubling the amount of rectangles now from what used to be 4 to 8. You don't have to double, you can go any other number higher than what you had before. Now, I'm going to draw on the first one right-hand sum for the all case. You see? That's the old case. And everything that you see here is error. And every single one from the old case will have that type of the error. But look at the new case in blue. The new case is actually having a rectangle there and having a rectangle there. Do we see that? So all of this area that used to be error before is no longer error. Right? I had to zoom into this so you can see. This is still the same picture, except before when you had 4 rectangles, now with this blue, we have less rectangles. And those rectangles have less error than the red ones before. So all of this area now, this area here that used to be error is no longer error. There's another one here and another one on top of this one and another one, right? They had this area as error and is no longer error. But it's never a free lunch. What do we have to do? Less error. At what cost? More calculations, exactly. More calculations. So these are the right-hand sums now. And these right-hand sums have what? Right-hand sums, we have that the area R is going to be square root of 3.5 times 1/2. Remember our delta x? Our delta x is now not 1. Our delta x is now 1/2. All of these are delta x's. They used to be 1 because they used to go from 3 to 4. Now it goes from 3 to 3.5. So delta x is now half. The next calculation is root of 4. Oops, plus. I didn't hit the shift over there. 1/2 plus 4.5 times 1/2 plus square root of 5 times 1/2 plus square root of 5.5 times 1/2 plus square root of 6 times 1/2 plus square root of 6 times 5 times 1/2 plus square root of 7 times 1/2. Now I hope you see that you can actually, for this calculation, factor out 1/2 so you don't have to compute this forever. and then just do the square roots first. This is where I dread that I ever started doing this. I start I'm almost done. There we go. So I have 18.22. And then I cut that in half, and I get 9.11. That's better. Better than 933 from before. So, more rectangles, better precision, but also more work. Now, when you ask Mathematica and other software to do the definite integral and find the area under the curve, they can run this on 10,000 rectangles for insanely good precision, right? Because it's a computer, just plows through the calculations quickly. So, to get better results, use more rectangles, i.e. better resolution. Do we have to gravitate and have this around 1 unit or half a unit in terms of rectangles for delta x? The answer is no. You see, we can partition the interval with any number of rectangles. It doesn't matter. The formula says that delta x is equal to b minus a over n, where n is the number of rectangles. So, as example, say you're on interval 1 to 7 with n equals 5. I don't think I can make any more annoying than this. Probably I could, but So 5 rectangles on the interval 1 to 7. Good. So this is number 1, and the end 7, 1, 2, 3, 4, 5 rectangles in between. We compute delta x, because in between each one of these is delta x. So you have 5 delta x's there because you have 5 rectangles. So delta x is going to be 7 minus 1 over 5, which is 6/5. That's 6/5 right there. So what's the first number? First next number has to be 2.1. I mean 2.2. 2.2. Because delta x is 1.2. You keep adding 1.2 to each point. So 3.4, 4.6, 5.8, and then plus 1.2, it lands into 7, and there's our partition. So delta x can be anything It doesn't have to be 1 or a half. It can be any value. Your job is to compute the function at that value, whatever you get, and multiply by delta x, in this case 1.2. So what is the summary of this section now? The summary is that we can approximate the area under the curve by simply adding all of the areas, and now we have this funny symbol. We have this funny symbol that you might have not used before, and this symbol is means sum, add. That's what the symbol means. Now we'll talk in details about the symbol now. So now I know that each area is actually f computed at all of these intervals times delta x from 1 to n. And that's how we approximate the areas. We approximate the areas by figuring out individual rectangles, right? And then we add them all up. So now, if you want to dissect this notation, this part is individual areas, and then this is over here sum of. So that's how you understand this formula. You see now I is a counter, and in this case I starts from 1, goes to 2, 3, 4, 5, and so on, which is now asking us to go and cover this summation notation in detail. It used to be a part of pre-calculus course, but then education deteriorated. So now let's talk about middle school concept here. So I understand it's a new symbol, it's a new thing. I already said it means add. And if I just simply go and say I equals 1 to 5, and I just say I over here, you keep replacing values. So first time around, the counter starts here and ends there. So first time around, I is taking a value of 1, and then there is a summation symbol, so it's plus. And then the next time around, it's like a loop in programming. It's taking a value of 2, plus 3, plus 4, plus 5. 5 is where it ends. So all of this adds to 15. So sum of I, when I goes from 1 to 5, is equal to 15. There is now freedom to plug any formula inside this summation, like I squared minus 1. No, plus 1. So I'm using summation on I squared plus 1. Well, we are starting at 1. So 1 squared plus 1, plus from the summation, 2 squared plus 1, plus 3 squared plus 1, plus 4 squared plus 1, plus 5 squared plus 1. So you are using the formula, whatever is given to you, you are using that formula, and you are plugging in the counter values 1, 2, 3, 4, 5. Now clearly this counter could be, 3 to 17, could be 0 to infinity, as we are going to have it. So it can be any values in there. And now just go and you compute. 1 squared is 1 plus 1 is 2, plus 5, plus 10, plus 17, plus 26. and then you add them all together. So these are what? 43, 45, 50, 60. I hope. Right? 43, 45, 50, 60. Good. So summation symbol just means keep adding the terms over and over and over again. There's another one, there is pi, and that's multiplication. We don't cover that one in calculus at all, but if you have pi, I goes from 1 to 3, of, let's say, square root of I, you will get square root of 1 times square root of 2 times square root of 3 to get square root of 6, right? We don't cover this, so not in calculus. I'm just going to erase this, but I just want to mention that, you know, these notations exist. So, you know, there's one for summation, one for multiplication as well. So we are allowed to plug in any values, any formulas within the sum, and then the values come from the counter. I goes run to 5. So now, does this help our old problem? With notation. On 3 to 7. And the answer, yeah, it does. There is an easy way to write the entire problem by stating that you're summing values 3 to 7 of square root of I. So that's root 3 plus root 4 plus root 5 plus root 6. If you remember, this was the first iteration with 4 rectangles, which we did. I believe we got 8.45 or 42 or something like that. So you can see this is just a notation to helps us write things more compact, faster, easier. So now, I will ask you to compute, so approximate area for f of x equals to ln of x plus 1 on 1 to 7 using 4 rectangles, and then using 6 rectangles, and then using 9 rectangles. So first two should be very quick. The last one should be annoying and long. Go. I should have assigned left side of the classroom to the left sums and the right to the right sums, but I forgot. It just occurred to me. That's what I do every time. These guys left sums, these guys right sums. You probably will do left sums. Probably.
Are we actually going to use these figures? Are we just going to use integrals for figures? Will we use these two? I like that.
So if you play the role, plus if you're programming your computer, do this, they don't understand that the role exported executed computed between the links and so. You have to do this with 10,000 recommended algorithm and loop, and that's it.
Relax.
All right, let's take a look at this together. So the first case, let's call them A, B, and C. I don't know. So for part A, I have n equals to 4. So if I'm on the interval 1 to 7, I'm always on the interval 1 to 7. So delta x is equal to 7 minus 1 over 4, which is 6 over 4, which is 3 halves. It's 1.5. I like to draw the partition. 1, 2, 3, 4, 5 numbers are 4 rectangles. I start at 1, and then there's 2.5, and then 4, and then 5.5, and then 7. So these are the numbers that I have to use, because these are the numbers that are partitions, right? Each one of these has a delta x in between, which is 1.5, 3 halves. So now, the left areas are going to be, I have 3 halves times, now left. This is the left, this is the left, this is the left, and this is the left. Those are the 4 lefts. So I have function computed at 1 plus function computed at 2.5 plus function computed at 4 plus function computed at 5.5. Maybe I should use these brackets. So this is 3 halves times, and now what do I have? ln of plus 1, right? So it's ln 2 plus ln 3.5, right? Because the formula is x plus 1. ln 5 plus ln 6.5. And now we compute these values, and we have the left sum. Going to plug all of this at once, so ln 2 plus ln 3.5 plus ln 5 plus ln 6.5. I already see that I made a mistake plugging in this into calculator because I didn't close the parenthesis after. .5, there we go. So 8.14. Now for the right hand sums, AR, we still have 3 halves, but now I start at 2.5 and I go to 4. It's f of 5.5 plus f of 7. And now the calculation is the same. So ln, except this time I have 7.5 at the end. No, 8 at the end. So I'm going to call the previous calculation and replace the first ln, which was ln2, with ln8. 10.22. So the true area is in between 8.14 and 10.22. But I can do better. So now we're going to do easier case with n equals 6 on 1 to 7. So now that partitions perfectly. You start at 1, and then 2, and then 3, and then 4, and then 5, and then 6, and then 7. Because delta x is 1. 7 minus 1 over 6 is 6 over 6, which is 1. So now the left sums is going to be 1 times f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. We do not use the 7 on the left sums because there is no rectangle to its right, so that it can be the left for that rectangle. So this is ln2 plus ln3 plus ln4 plus ln5 plus ln6 plus ln7. Remember to close parentheses after every ln. .53. And area to the right is going to be the same thing except no ln2. So we start 1 times, which is delta x, and then we have ln3 plus ln4 plus dot 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 plus ln8. So I'm going to call the previous calculation and replace the 2 with 8 and get 9.91. So now I know that the actual area is in between 8.53 and 9.91. That's better than 8.14 and 10.22. So you see that it gets better. It's a smaller range. Now we had more calculations. And now part C, the most annoying one. Who picked 9 rectangles? N equals 9 on 1 to 7. So delta x is equal to 7 minus 1 over 9, which is 6 over 9, which is 2/3. So now our partition is going to have 9, 2, 3, 4, 5, 6, 7, 8, 9. So we start with number 1, and then this is 2/3, and then a 4/3, and then 6/3, which is 2, and then 8/3, and then 10/3, and then 12/3, which is 4, and then 14/3, and then 16/3, and then 18/3. I lost it.
How'd you go from 1 to 2/3?
Yeah, I have no clue. Back to the drawing board. You start from 1. So it's 1 and 2/3. So this is 3/3. So then you have 5/3 plus 2/3, it's 7/3, plus 2/3, it's 9/3, which is 3. And then 11/3, and then 13/3, and then 15/3, which is 5, and then 17/3, and then 19/3, and finally 21/3, which is 7. There we go. Now someone has to compute this. So left areas are going to be 2/3, which we can factor out, our delta x. And now you have left sums. So ln2 plus ln of 8/3, because it's plus 1, right? So 5/3 plus 1 is 8/3. And then plus ln of 10/3. And then plus, that's 3 plus 1 is for ln 4. And then plus ln of 14/3. Plus ln of 17/3. Plus ln of 6. Plus ln of 20/3. Plus ln of 20, so plus 3, right? 22/3, and finally plus ln of 8. Pain? Hold on, we are warming up. You did class prep for 5-2? I can tell. If this is tiring, then you haven't done 5-2 class prep yet. ln 2 plus ln 8/3. Oh, nightmare. It's not big nightmare. Plus ln 10/3. Plus ln 4. Plus ln 14/3. Plus 17/3. 17/3. Plus ln 6. Plus ln 20/3. Plus ln 22/3.
You start shouting random numbers.
Plus ln 8. Bingo. Is that what you want here? 10.2. Exactly. Well, not exactly, but 10.2, and then it goes 3 zeros, and then 2, 7, 2, 4. So left-hand sums ended up being 10.2. Right-hand sums now. Still 2/3. And I'll say ln, and instead of 2, we're not using 2 anymore. We are using, this is 22, then 24, 26. So that's 76 over 2 plus old. Terms from there. So now in my calculator, I just go second entry, and yeah. And instead of ln 2, second insert, 26 over 3. Oh, I put over 2, 3. 11.18. So true area here is between 10.2 and 11.18. So if I write all three ranges, here is the 10.2 less equal than area less equal than 11.18. Then the previous one was 853, 991. Well, I don't like this. Something is wrong. 814, 1022. Something is wrong. This number is bad. It has to be in between 10 and 11, and can be 991. So something is wrong with that number. What you're supposed to see from this blue chart is that these numbers are racing towards a value. These numbers will be falling this way towards a value, and then the value must be in between, right? When you look at the precision.
Did we mix up one of the left-hand sides and the right-hand sides?
No, there was a calculation error of some kind somewhere over here. I don't like this number. 991. It didn't fall. There are definitely some calculation errors here. Definitely calculation errors, because they should line up. Increasing over here and decreasing over there. I mean, yeah. To give you this good squeeze of it. Unless I copied something wrong, but yeah, they look good from over there. So if you redo these calculations, you should be able to find what's wrong. But I don't like the way it's... This 991 should not be in the middle. It should be number in between. So it's in increase. Like over here, over there as well. Okay. So,
something I noticed, is it really getting better as you increase?
yes.
They all seem to be the same distance away. Like from the, as we go down, I don't know.
Well, I would have to actually get the exact one to see what let's see. Was it from 1 to 7? So when Wolfram Alpha does 5,000 of these things, it works out to be 925. So this number is not good either. That might be 9.2, not 10.2. But 925, and this 925 needs to be in between every time. So this is probably 9.2 over here. So I probably forgot to close a parenthesis or something in the calculation somewhere. Yeah, something is off, but if you redo the calculations, it will fall in. So it's just labor intensive, that's all it is. You pick left sums or right sums, no matter what the function looks like. So even if you have like whatever kind of function, let's say you're going from here, which is your A, there, your B, you can partition, and then some rectangles will be underneath, some will be above, some will be underneath. It doesn't matter. So some of this error, right? So this one maybe cancels that one. They don't cancel exactly, but it's both above. So I don't know. So it would be, right, if it's a wavy function like that, a lot of cancellations. But it's important to keep the left or the right fixed throughout the entire problem. And that's 5.1. There are also formulas for sums which we are going to use, but those formulas we're going to use in 5.2, so I didn't talk about them at all. They talked about those, they presented those formulas when they talked about the summation notation. So on page 340 they give you these formulas, but I'll talk about them in 5.2. So let's take a short break, and then 5 minutes or so. 5.2, the definite integral.